Okay, so can I present my presentation?
Yes.
Okay, so I am very glad that I have this opportunity to present my talk, and as you can see, this talk is focused on the errors in variables measurement model, and I will mention very briefly potential applications. My talk is very closely related to previous presentation at the IMECO conference in Hamburg, but I hope that many people here at this conference will be interested in this topic. So, yes, I need to change. I cannot move somehow. The next slide. Okay, can you see the next slide?
Yes, we see.
Okay, so the motivation is as presented here. A measurement model constitutes a relationship between output quantities or measurements and the input quantities involved in the measurements according to GAM. Part 6, it means it is the part which is focused on developing and using measurement models. It provides detailed insight into construction and the utilization of measurement models. In my presentation, I would like to address the above mentioned specific challenges. What is specific is that we employ the statistical errors in variables approach or measurement model. The goal of this presentation or this research is to develop a unified modeling approach which is consistent with the basic GAM principles, but also that is applicable for a wide range of measurement problems along with the algorithmic implementation. The suggested modeling approach has been successfully applied to various scenarios, including nonlinear errors in variables regression, straight line and polynomial calibration, ellipse and ellipsoid fitting for the modulating interferometer signals, and many more. What is the errors in variables measurement model? The suggested errors in variables model is expressed as a combination of symbol model of direct measurements. It is expressed in this part, the first part. X represents the measurement results, mu represents the true values, epsilon are measurements errors, and there are some restrictions, Q restrictions, which consist restrictions on the true values of the measured input quantities. Plus, there are another parameters beta which interconnect those true values, and those restrictions are expressed in the following form as an implicit equation. Capital F means Q dimensional vector of outputs, and the inputs are mu, the true values of measured input quantities, and beta are other parameters which are true values of our measurement. This is explained here, but I would like to generalize this approach that instead of direct measurements, we could also consider indirect measurements. Here is the result, the difference. Here we measure directly some parameters mu, the true values, but here we could measure some functions of unknown parameters theta, say. So it is indirect measurements, this case, and this is the direct measurement case. I'm not talking about the indirect measurement case because it is much more technically complicated, but I wanted to say that it is possible to consider also this generalized version of this errors in variables approach. So again, in the generalized version, we are measuring indirectly some values which are functionally depending on parameters theta, and those true values could be very complicated way related with other parameters in such a way. I would like to start with a simple example which I found in currently published paper in Metrology and Instruments by author Bocura, Zadorozhna, and Zakharov, and they are considering measurement uncertainty evaluation of object coordinates in plane by goniometric method. In this example, the authors consider that they want to identify the position of the point P, the values or the position is given by xp value and yp value, and we have several measurements, direct measurements of input quantities. We directly measure the coordinates of point 01 and directly measure coordinates of point 02, and we measure also some angles alpha 1 and alpha 2, and based on goniometric relations we can construct some restrictions on those directly measured parameters in such a way, and fortunately in this case we can find some exact solution because if we put it together, so we can find the exact solution, which is given here in this equation. But in much more complicated situations, we can also imagine that in much more complicated situations, it is not easy, or it is even not possible to find exact arithmetical or mathematical solution, and we should rely on numerical solution. And it is exactly what we are discussing in my contribution. For instance, let us assume that for given illustration, we consider the so-called two-variate errors in variables model, where we construct measurement vectors of x's and say y's, but I am denoting them x1 and x2 with true values mu1 and mu2. Those are vectors, and those vectors are interconnected by function f. A very simple example of such model is a straight line calibration function. If you imagine that mu1 represents true value of x's, mu2 represents true value of y's, and we have intercept and slope of the calibration line, straight line, so we can say that the true values are interrelated in the following functional form. So we have directly observed measurements of x's and y's, say, and we know that true values should fulfill this functional restriction, which says that those true values lie on the line. Similarly, we can consider another much more complicated functions like functional polynomial function, fractional polynomial function, where we consider not simple polynomial but fractional polynomial. Fractions means there are some fractions of the input quantities, and beta 1, beta 2, beta 3, beta 4, and beta 5 in this particular example represents the parameters of this fractional polynomial. Mu1 represents the x's, the true values of x variable, and mu2 represents the true values of y variable. Our measurand or parameter of interest are, of course, the parameters of this polynomial, this fractional polynomial. Similarly, in other technical quantities like nanometrology, we consider nonlinear functions. We can also consider nonlinear functions like Oliver-Farr function in atomic force microscopy or indentation problems, which is used for fitting the data. And here we have nonlinear relationship between true values of x's, true values of y's, and there are some parameters which are our measurand, parameters of interest, which are denoted by beta 1, beta 2, and beta 3. And the last example which I would consider is the fitting of ellipsoid. And ellipsoid is given by the following geometrical or algebraical equations for ellipsoid, and mu1 represents x's, mu2 represents y's, and beta 1, beta 2, beta 3, beta 4, and beta 5 represents algebraic parametrization or parameters of algebraic parametrization of this ellipsoid. So this is also another function which could be expressed in this general form, and we could use this approach to model such functions. So what is the objective of our problem? The objective is to identify the best estimates of parameters mu, the true unknown values for us, and the parameter of interest, which I am considering that they are our measurements. The criterion for doing that is minimization of total sum of squares, which is subject to some restrictions. Those restrictions are expressed here. The lambda represents the Lagrangian, and this is the generalized sum of squares, where U represents the general uncertainty matrix. So those direct measurements could be interrelated by some variances, covariances, uncertainties, and so on. So this is the problem which is considered to be solved. What is the key point of our approach? The method is built upon the optimum estimation procedure, which is known in statistics as best linear unbiased estimation, and it is in linear regression models with linear constraints, and it is of course based on very well-known Gauss-Markov theorem. Our approach considers not only linear restrictions and linear models, but it is generalized to nonlinear models with nonlinear restrictions, but it is based on iterative linearization of these models. So our procedure is iterative estimation process, which leads to not best linear unbiased estimations, but we are saying locally best linear unbiased estimates, which are optimal in local point or a region around the estimated values. We have implemented this approach also algorithmically, or implemented it as an algorithm, and the name of this algorithm, which we have developed with our colleagues from Czech Meteorological Institutes, is called Optimum Estimate of Function Parameters by Iterated Linearization. In abbreviation, it is OFPIL, and it is implemented in various environments such as R, MATLAB, C, and the last version, which is planned to be realized, is also in Excel as an Excel macro. So how it works? Now I will give some technical details. Maybe it will be not easy to follow the technical details, but anyway, I would like to present some technical details. So once again, our model formally could be expressed in the following form. Here, the first part...
Halo?
Sorry?
Słyszę, a nie widzę. Nie wiem, jak wyłączyć widzenie.
It is not visible?
Ja mam...
I'm sorry. Should I... I'm sorry. I don't know if it is visible or not. Can you
Yes,
see
yes,
some?
yes, visible.
Yes, visible. Yes, visible.
Okay. Still? Is it visible?
Yes, yes.
Okay,
Yes,
so I'm following. My equation, as I already explained, is that first part is direct measurements. It means we are directly measured input quantities. They have some unknown values here denoted as a vector mu, and some measurement errors, and we have some restrictions expressed, restrictions on the true parameters. Of course, those true parameters are unknown. So what we are doing in each step, we iteratively linearize the model, and each iteration step we linearize the nonlinear model at specific parameter values. We should start somewhere at mu0 and beta 0, and then apply in this linearized model the blue procedure. It is best linear unbiased estimation procedure locally in this linearized model. This is technically how we linearize the model. The measurements delta x represents x after subtracting this initial value mu0. Delta mi represents the unknown parameter after subtracting mu0. Delta beta represents the parameter beta, our measurement, after subtracting the initial value beta 0, and the matrices b1, b2, and vector b0 are derived from the restrictions by calculating the partial derivatives. First, with respect to the parameter mu, the vector parameter mu, and evaluated the initial values. And the second matrix is the partial derivative of this set of restriction or function of restrictions with respect to the parameter beta, and evaluated the initial values. Similarly, the beta 0 is the final vector, and it is nothing else than the function of restrictions evaluated at the initial values. So now, this is just to illustrate that calculation of such in each iterative step, it is not so complicated. It depends on some technical details. We should linearize the model. We should calculate the matrices beta 1, beta 2, and b evaluated at the initial values. Then we should calculate holistic decomposition of this matrix, which is related to the uncertainty matrix. we should calculate or solve a linear matrix form using triangular solve procedure if it is available. Then we should calculate QR decomposition of this matrix E, which is solution of the previous equation. And finally, we should evaluate auxiliary matrix Q, which consists of those submatrices. And finally, if we calculated this matrix Q, we can evaluate the best estimate, locally best linear unbiased estimate of the unknown parameters of the input quantities, which is expressed exactly here. And similarly, we can evaluate the best linear unbiased estimator locally at the initial values, which is given exactly here. We can also calculate directly the covariance matrix or uncertainty matrix of this estimated measurand or estimated parameters beta, which is directly given as a negative part of the Q22 matrix, which is given here. So everything is clear. It is not easy to follow on presentation, I know, but I just wanted to express you that the calculation is relatively easy. It could be calculated in such software like MATLAB or C or even in Excel in relatively very easy several steps. Those algorithms have been implemented, as I already said, and they are freely available. For instance, the OFPL R package is available in those addresses. The C implementation in language C, it is available at GitHub or GitLab address, GitLab at this address. And the MATLAB version, which I am author of this MATLAB version, is available at GitHub at my link. And if you will look through Google for OFPL MATLAB, you will find directly this link where it is completely implemented. So I would like to finish by a very short discussion. This model approach shows great potential across various domains, but it is important to recognize, of course, some limitations. The convergence of the proposed method is not universally guaranteed. It is much because those problems are very complicated in general, and the optimality of the resulting estimators may only be local. It is not general global solution. Despite these challenges, the extensive testing across diverse applications and comparison with other methods and algorithms have demonstrated its practical effectiveness. In metrology, the stated uncertainty matrix often relies on expert judgment. Our previous studies have shown that it is crucial to verify the adequacy of the selected model and the specified uncertainty matrix against the observed data, because if the uncertainty matrix is too generous, I would say, the algorithm could have some problem with convergence. Extensive testing has confirmed that parameter estimation through iteration is effective and aligns well with Monte Carlo methods, which are known from supplement 2 of GAM and supplement 1 and supplement 2 of GAM, and particularly when the measurements models is, so we are saying from mathematical point of view, weakly nonlinear. What does it mean? Weakly nonlinear models are such models when the curvature of the constraint function is relatively small and the uncertainties associated with the direct measurements are also relatively small and weakly correlated. So if this model is, we say, nice, weakly nonlinear, so the algorithm works very perfectly, but in very complicated curved model, we could meet with some problems with convergence and accuracy. So to conclude, the errors in variables measurement model integrates constraints that capture the relationship between the true values of input and output quantities. This model effectively represents the measurement process. In most practical situations, the OFPL algorithm, through iterative linearization, provides reliable estimates of model parameters, and this combination marks a significant advancement in addressing complex measurement problems, improving both accuracy and reliability across various applications. As I already said, the OFPL algorithm may not always guarantee convergence or optimal solution, but it offers a straightforward and efficient method to manage complexity through iterative refinement. And finally, a notable advantage of this approach, and particularly the OFPL algorithm, is its ability to seamlessly incorporate complex models and general uncertainty matrices, making it, according to us, a versatile tool in methodological applications and analysis. So I would like to thank you very much for your consideration. Thank you.
Thank you, Victor, for your interesting presentation. Especially thanks for your mention of my
Yes, it is very interesting topic, and I must say that it is not only possible solution to this problem. You can find many relations, goniometric relations, and the question is which is the better, which is the optimum, which could lead to optimum solution. I'm not sure if you have considered in your paper the general uncertainty matrix, if the measurements are interrelated, because they are measured by the same device, for instance. So they are naturally interrelated. They have common uncertainties and they have some covariances. So this is which should be considered in much more complicated models. So it is what I wanted to say. But the problem is very, very interesting.
Yes, thank you. We have several articles for this problem, and I can send you it for your Alistair Forbes in Zygmunt Warsha. Please, your questions.
Victor, do you calculate correlation coefficients from the measurement data online?
You know, the uncertainty matrix is considered in this approach that it is given, and of course you know that the uncertainty matrix is derived by type A methods and type B methods. So it is very tricky, and we consider it as a known matrix. So for the input quantities, of course, the resulted uncertainty matrix for the output parameters or output quantities is calculated from the inputs.
Thank you.
Alistair, please.
Yes, thank you very much, Victor. How does your algorithm relate to sort of standard optimization approaches where you're trying to minimize a function subject to nonlinear constraints, and you go about linearizing the constraints, maybe a quadratic approximation to the function you're trying to minimize, and have a sequential sort of quadratic programming approach to solving that problem?
I'm not sure if I understand very well your question, but I understand that this is based on a linearization of this model, as I explained in each step. And in each step, we apply Gauss-Markov theorem to find optimal solution.
Okay, yes. Okay, so it's a sequential Gauss-Markov.
Yes, yes.
Okay, yeah. Okay, thank you.
Thank you. Dear colleagues, do you have any question to Victor? Victor, no question, unfortunately. Thank you very much for your presentation.
I'm sorry for maybe being a little bit late, but I didn't understand very well what is the starting time of this conference. I was misled 1 hour later.
Yeah, you are late for 1 hour.
Yes. I'm sorry.
No problem.
Because that's Ukrainian. That was in Ukrainian time.
Yes. Now I understand.